Hello, we are looking at chapter 4, or unit 4, I should say. AP Chemistry Unit 4, Chemical Reactions. So this should be a pretty quick unit. A lot of stuff that's review. Enduring understandings. A substance that changes its properties or that changes into a different substance can be represented by chemical equations. When a substance changes into a new substance or when its properties change, no mass is lost or gained, and a substance can change into another substance through different processes, and the change itself can be classified by the sort of process that produced it. All right, so this first enduring understanding, okay? When a physical change occurs, we're gonna get changes in, like, about the substance, but we're not gonna get a change in composition. So here would be an example of a substance diffusing, right? It's spreading out, so we're gonna have different properties, but it is not a new substance. Another classic example of a physical change is a phase change, right? From solid to liquid to gas, separation of mixtures, all things like that. Now, in a chemical reaction, we're going to make a new substance. That's the important part, all right? Different composition, a new substance, and there's four big indicators: production of heat or light, formation of a gas, formation of a precipitate, and or a color change, right? Those aren't the only indicators, but those are four really good ones that let us know if a chemical reaction has occurred and if we have made a new substance in the reaction. All right, now all physical and chemical processes can be represented symbolically by balanced equations. All right, lots of information in an equation, very important. You have your reactant and your products. You have the formulas, right? The formula unit for the ionic compounds, for the molecules, the physical states. You have the subscripts throughout, the coefficients. So make sure you know all those things, right? When we balance a chemical reaction, we change coefficients. We never change subscripts. And if it's a physical change, it'll have the exact same formula before as a reactant and as a product to show that it's not a new substance. All right. Now, it must be equal numbers of atoms for before and after a change occurs. So sometimes when we're balancing an equation, we use a chart, right? So this one is not balanced yet, right? So we would need to make sure that the ions equaled each other. So we would need 4 irons as a product. We would need 3 carbons as a reactant, right? So every atom, every number of atoms as a reactant has to be present, and the number of atoms as products. And what that will do is it will allow for the mass to be conserved. In every chemical reaction, law of conservation of mass, the mass of the reactants is equal to the mass of the products. It may be, it may not seem that way in a reaction where you have a gas, and so the gas is not in a sealed container, it just leaves, but mass is always conserved. All right, we have molecular, complete ionic, and net ionic equations, all right, and we use them in different situations. So you have an example of all 3 here. The molecular equation, everything is written out as a molecule. If it is an aqueous substance, which means it has been hydrated, it means that there is water completely surrounding it. If it's ionic and it's aqueous and it's hydrated, the ions will have split apart in that dissolving process. So we can write the complete ionic equation where anything aqueous is split apart if it's ionic, and then anything solid stays as solid. And then the net ionic removes what we call spectator ions. All right, chlorine is an example of a spectator ion. It looks exactly the same as a reactant and a product. So we can see the chlorine didn't change. It's not part of this reaction that includes calcium and carbonate forming a solid. All right, and here we can see how calcium and carbonate look different as reactants than they do as a product, because there's that different state. Now it's solid. They were free ions. Now they're a solid. All right. Now, net ionic equations. I'm always kind of disappointed when kids tell me, like very late in the year, they have no clue how to do a net ionic equation. So if you do not know how to write a net ionic equation, make sure you practice that this week, right? Because it's assumed that you know it. It's assumed that you can interpret that information. The big thing about a net ionic equation, you cannot do it if you don't know how an ionic compound dissociates. All right, we'll see this again in Unit 7. So you'll see it later in the year as well with the KSP, the solubility of salts. but basically, if it's an ionic compound, the subscript of an ion ends up becoming its coefficient. All right, so since it's calcium chloride CaCl2, we get 1 calcium, we get 2 chloride ions. So that's an important piece. All right, so here would be a trickier one, K3PO4, we would get 3 K pluses. The PO4 would stay together as that polyatomic ion. You don't have to have memorized all the polyatomic ions, but you should be very comfortable with seeing them. So it's always oxygen with another element for the majority of the polyatomic ions. All right, but it's all context. When they say the form used to represent the reaction depends on the context in which it is to be used. All right, net ionic equations are going to be important in any aqueous reaction, specifically ones that form a precipitate. We will always get the same net ionic reaction, or are very similar ones for acid-base reactions, and redox net ionic can be pretty important because those are happening in solution. But we would not use a net ionic for a combustion or a synthesis or a decomposition reaction. All right, balanced chemical equations in their various forms can be translated into symbolic particulate representations, right? So we see synthesis, we see decomposition, single replacement, double replacement. All right, these are using hypothetical elements. Sometimes we can get real elements, right? So we have a reaction going on here. This reaction is very nice to us because it is in a perfect stoichiometric ratio. So these blues are their doubles, right? The reds are singles, and we have exactly 4 of the blues, and we have exactly 8 of the reds. So they get together very easily. Sometimes we get these symbolic particulate representations, and the AP, the College Board, does like this, where there is an excess of one of them. And so in the representations, that excess needs to be shown. So anytime, and I will say this for any particulate representation, the number of particles drawn in the pictures that you're given is deliberate, right? So you need to take that into account. You should always kind of itemize that quickly when you look at these diagrams. And if you have to draw an after, if it's like a before and after chemical reaction thing, and you were supposed to draw that excess and you don't, you just got that question wrong. So always look at what's going on. This is H2 plus O2. And if we think about the reaction that's going to form, it's forming H2O. It's going to be 2 H2s for every 1 O2. So we have 6 of each, but since it's a 2-to-1 stoichiometric ratio, and we'll see that in later slides, we end up with that excess oxygen. So just be careful. These particle diagrams, everything is deliberate about them. The spacing, everything. Anytime you are given the picture, it's deliberate. Anytime you're asked to draw a picture, that's what they're looking for, that attention to detail. All right, processes that involve the breaking and or formation of chemical bonds are typically classified as chemical processes. Processes that involve only changes in intermolecular attractions, such as phase changes, are typically classified as physical processes. All right, breaking bonds, forming new bonds is always a chemical reaction. This is obviously not what it looks like. This is a very crude drawing, and since we're talking about breaking bonds and forming new bonds, I have to state breaking bonds is endothermic. You always put in energy to break a bond, and then energy is always released when a new bond is formed. All right, where those energies line up, it can still be endothermic or exothermic if it takes more energy to break the bond, or if it releases more when the bond is formed. But this is a misconception. A lot of kids have it backwards. They think energy is released when a bond is broken. That is not true. It requires energy to break a bond. All right, now here's a picture of liquid, of water boiling, right? So it's still water. The particles are still water, but now they've spread out. The intermolecular forces between the molecules have been overcome. So that is an important idea. In these physical changes, chemical bonds are not being broken, just intermolecular interactions. All right, so yes, it's breaking apart the hydrogen bonding, but that is not a chemical bond. That is an interaction between polar molecules. So that's what's happening when water boils. Sometimes physical change processes involving the breaking of chemical bonds. For example, plausible arguments could be made for the dissolution of salt in water as either a physical or chemical process. Involves breaking of ionic bonds and the formation of ion dipole interactions between ions and solvents. All right, so dissolving salt, we would traditionally say it's a physical change. You could make the argument that it's a chemical change. All right, I don't think that we're going to have a debate on this for the AP exam. Just one thing to keep in mind: if you dissolve salt, you break apart that lattice, but that lattice can recrystallize if the water was driven off. All right, the salt ions will form that lattice on their own once the water is removed, so it will go back to that form. All right, now because atoms must be conserved during a chemical process, it is possible to calculate product amounts by using known reactant amounts or to calculate reactant amounts given known product amounts. So this is stoichiometry. All right, so whatever you got to do to get to moles of given, right? If you're going from atoms, ions, or molecules to moles or grams to moles, but you can use a mole to mole ratio to go from reactant to product. And then once you have the moles of your product, you can make whatever change you want. All right, I like the railroad track stoichiometry bridge. I think it's very helpful, especially for a straightforward stoichiometry question. It allows you to move real quick. Starting mass, 1 mole over the molar mass of the starting substance. Coefficients, coefficient of what we want over coefficient of the given. Molar mass of the substance asked for over 1, answer in grams. This track always works. So it allows you to move quickly, right? And sometimes being able to answer questions very quickly is a very important part of being successful on the AP exam. All right, now the coefficients of balanced chemical equations contain information regarding the proportionality of the amounts of the substances involved in the reaction. All right, so this is the mole ratio, right? The mole ratio, it's always a fraction, and you can put any two parts of the reaction. So it can be reactant to reactant, product to product. Typically, we do reactant to product. You could set them up in all different ways, right? So for this one example, we can get 3 different mole ratios. But the point of a mole ratio, it's to be used as a conversion factor. So it's important that you always think about, as you're working through a stoichiometry, you want to reach a point where whatever substance you are given, you can get to the moles of your given, and then you can use this mole ratio, the coefficients from the balanced reaction, where you want to set up the unit you want up top. So that'll be the coefficient of the substance you want to find divided by the coefficient of the unit you've already been given. And I always say this to kids, right? It's always want over given. You prioritize what you want and you use what you were given to get it. All right, so keep that in mind when you're doing your stoichiometry. And these stoichiometric calculations, they may involve the ideal gas law, they may involve molarity. So if we're using the ideal gas law, PV equals nRT, we can solve for N. We might use the ideal gas law at the beginning of a stoichiometry question to get the moles of the given. We may be using it at the end of a stoichiometry problem where we use the stoichiometric, the mole ratio to find the moles of a desired product. And that may be a gas. So then we would use the ideal gas law to solve for either its volume or its pressure or maybe its temperature. Now, if we're at STP, we get to use the easy conversion, 22.4 liters equals 1 mole, and that's for any gas. All right, so we can have 22.4 liters of oxygen at STP. That would be the same as 32 grams of oxygen, right? Because they're both 1 mole. So that's an easy conversion. And if we're doing a chemical reaction where it's all gases, if they're all at the exact same conditions, you can use the mole ratio as like a liter ratio because they have a direct relationship. So you could say 2 liters of this gas react with 3 liters of that gas, right? If it's a 2 to 3 mole ratio, if they're both gases at the exact same conditions. All right, as far as molarity goes, it's just another way to get us the mole, right? So molarity is moles of solute divided by volume of solution. So typically, when we're doing a stoichiometry with molarity, we're doing molarity times volume, right? So let's say you're given a certain volume of a certain molarity substance reacting maybe with excess, you're going to do molarity times volume. Now you have your moles, and now you can use that with the mole ratio, and you can continue onward with your stoichiometry. All right, so if it's a mass to mass problem, you can use the railroad track. The beginning and end of the railroad track may change if we're looking at an ideal gas law or if we're looking at molarity. All right, so that is our stoichiometry. That is something that we should be good at, right? Kind of looking at ionics. If you're weak in stoichiometry, you want to do a little bit of practice before the AP exam so you feel really good about it. All right, titrations. All right, titrations, we know that we have a burette. We know that the burette is a very precise piece of glassware. It's one of our best pieces of glassware. We can measure very specific small amounts of liquid, all right, and we can adjust it. We have the analyte always at the bottom. The titrant is in the burette. The known substance typically is always in the burette. So you have the known molarity and the known volume, so you can find the moles very well, and you always have to know the volume of your analyte accurately. Now, our typical titration is the acid-base titration, right, where we use the phenolphthalein indicator. There are other indicators, but usually use that one. It goes from clear when it's in the presence of an acid to purple when it's in the presence of a base, right? And we have a lot of fun with it. Lots of memes about it. I'm a big fan of just, I live dangerously. I had a lot of time and slow down when I get closer. And then like you're right there and you're excited, and then it gets way too dark and you're not excited anymore. We will see titration curves again in Unit 8, but I just want to point something out. In a titration curve, we have a gradual change until we reach the equivalence point, and that's why we get this really sharp vertical line. Right, so that's going to be an important feature of a titration curve. And it doesn't just have to be acid-base. We did a titration of iron pills at the beginning of the school year, where we titrate it with potassium permanganate, right, KMnO4. And that's a change where once the reaction has reached completion, one extra drop is going to completely change it from clear to purple because now you have extra permanganate. All right, so it doesn't just have to be acid-base for titrations. And again, the whole point of a titration, you can do molarity times volume to find the moles of the titrant, and then you can take the volume and divide it by, or you take that number of moles, do a stoichiometric ratio, whatever the reaction is for our acid-base, usually it's 1:1. But you can find the moles of the analyte that you just titrated and then divide it by its volume, and you would get the molarity. All right. Now, acid-base reactions, they involve the transfer of one or more protons between chemical species. So typically our acid-base reactions will be nice. It'll be H+, it'll be OH-, it'll make water. If they're not nice, NH3 is a very common base, and we'll talk about what that means in a second. But the H moves from the HCl to the NH3, right? So since a hydrogen has moved, this classifies it as an acid base, all right? Our strong acids, HCl, HBr, HI, hydrochloric, hydrobromic, hydroiodic, and then nitric acid, sulfuric acid, the first hydrogen, and perchloric acid, right? A lot of the strong bases are groups 1 and 2, lithium hydroxide, sodium, potassium, calcium, strontium, and barium hydroxide. All right. We will pick up more on acids and bases in Unit 8. So strong acids completely dissociate. Weak acids only partially do. They have an equilibrium. So we'll start seeing that in Unit 7 and then Unit 8. Something I want to point out. For the purpose of stoichiometry, any chemical reaction, any acid-base reaction, we will assume goes to completion when it's an acid in the presence of a base, right? So if you have a strong acid with a weak base or a strong base with a weak acid, the hydrogen transfer will go to completion, all right? And then whatever's left over, we'll see some complicated questions in Unit 8, but we don't have to worry about that for right now. We just have to write out the reaction and it will go to completion for our purposes of stoichiometry. All right, we also have oxidation reduction reactions, a couple of ways. I like the phrase oil rig. Oxidation is losing, reduction is gaining, all right? Losing and gaining electrons. There's Leoger. Now they're kind of changing it to Leo-Gosger. I liked it better as Leoger. It's just kind of a weird name, but loss of electron, oxidation, gain of electron, reduction. I don't know what ELMO stands for. I saw this, so if you can figure it out and that works for you, go for it. All right, but oxidation reduction reactions are where electrons are transferred. All right, and a good way to do it is to look at the oxidation numbers of substances in a reaction. So it's important that, first off, we know that in a redox reaction, electrons are transferred from the species that is oxidized to the species that is reduced. All right, so A here has 2 electrons, it loses them, it's been oxidized, and B has been reduced, it has gained them. But it's good to know the oxidation numbers, because the oxidation number of a substance that is reduced, its oxidation number gets lower. And the oxidation number of a substance that's been oxidized gets larger. All right, so elements in their free state are always 0. Technically, fluorine should be higher. Fluorine is always -1 in a compound. Oxygen is -2, except when it's a peroxide, which is when hydrogen's present. Hydrogen is always +1, except if it's in a metal hydride, which is -1. The sum of the oxidation numbers for a neutral compound is 0. That's important. The sum of oxidation numbers for a polyatomic ion equals the charge of that ion. And the ionic charge of metals is their oxidation number. So group 1 elements are +1, group 2 are +2. Transition metals can change their oxidation numbers. So iron 2 has an oxidation number of +2, iron 3 an oxidation number of +3. So if we go back to this reaction, we can see that the silver went from +1 to 0. Its number was reduced, so it was the element that was reduced. And reduction is gaining, is gained electrons. Copper has gone from 0 to 2+. It has been oxidized, and oxidation is losing, it's lost its electrons. All right, now a precipitation reaction typically involves forming an insoluble product. So here's where solubility rules come into play. What we've seen with the AP exam is often they give you the reaction and they identify the solid, so you don't have to. But it is good to know some of those solubility rules. Remember, nitrates are always soluble, so they very often end up with insoluble products later. So if you see something like lead 2 nitrate, all right, lead 2 nitrate, nitrate's one of the only anions that lead can be soluble in the presence of. All right, now lead 2 is insoluble in the presence of any chlorides, bromides, or fluorides. So that's why, or iodides, any of the halogens. So that's why I typically will start out with nitrate. Same thing like silver nitrate. Silver is a very insoluble compound, but it will be soluble in the presence of nitrate. So that will come about. And again, those solubility rules, they kind of make an appearance in Unit 7. We'll see it later when we talk about the solubility product of salts. All right, but this should be pretty straightforward. These are our net ionic reactions. Here's where we get our spectators. Things like potassium or the nitrate oftentimes will be the spectators in a reaction. All right, so we got the Pb2+, we got the 2I-, Pbi2 solid as our net ionic equation. And again, lead started off with the nitrate. We had the sodium iodide, double replacement, but the sodium and the nitrate are spectators and they get cut out. All right, a Bronsted-Lowry acid is a proton donor and a Bronsted-Lowry base is a proton acceptor. All right, the big thing with the Bronsted-Lowry definition for acids and bases, it expands on the Arrhenius definition, and Arrhenius is just hydrogen H+ and hydroxide OH-. Those two form water. The Bronsted-Lowry acid-base definition is good because it allows NH3 and these NH3 derivatives to count as a base. So when they interact with water, they produce hydroxide ions, but what ends up happening is a hydrogen moves from one species. We get these pairs, so a Bronsted-Lowry acid is always paired with the conjugate base. A Bronsted-Lowry base is always paired with the conjugate acid. All right, so the reaction can go forwards and backwards. It's an equilibrium. Again, topics that will be developed more later, but we should be able to identify a pair pretty easily. These pairs always differ by one hydrogen, NH3, NH4, right? It's differing by one hydrogen. And you know if it's an acid or a base, if it is gaining the hydrogen, it was the base, and if it's going to lose the hydrogen, it was the acid. All right. In aqueous solutions, water plays an important role in many acid-base reactions. So when we're using these acid-base reactions, we sometimes want water to be a reactant. Right? Oftentimes in an aqueous reaction, we don't list water. Right? Like in a precipitation reaction, we would not list water. But in an acid-base reaction, there's a good chance water will be a reactant. And we get these pairs, again, they're listing the conjugate acid-base pairs. Again, just think about they're always different by one hydrogen, right? So F minus HF, one hydrogen difference, so that's a base acid pair. Think about it, the F minus gains the hydrogen to become HF, that's why it starts out as a base. And when it's conjugate acid, if the reaction goes backwards, it donates the hydrogen. All right, and we can balance chemical equations for redox reactions from half reactions. You will not have to balance the whole thing, right? We sometimes see you can split apart the oxidation and reduction. You can balance them, and then you balance it for the electrons. Then you start to balance the oxygens with water molecules, and then you balance the hydrogen with hydrogens. We're only going to ever have to balance simple ones. So if you're writing out a half reaction, if it's reduction, you would write the element plus the number of electrons it gains, and then the product. The oxidation numbers should clearly change. If it's oxidation, you would write the compound, then the arrow, and then the product plus the number of electrons it lost. So a half reaction could look like this. Fe2 plus forming Fe3 plus an electron. Right, that's our oxidation half reaction. It has lost an electron. Ce4 plus the electron becomes Ce3 plus. That's my reduction half electron. Now, when I go to add these two reactions, I get both the reactants, Fe2 plus Ce4 plus, forming Fe3 plus Ce3 plus, both of the products. The number of electrons on both sides as a reactant and as a product should cancel. If they're not going to line up, let's say this was 2 electrons in the oxidation reaction, we could multiply this whole reaction by 2. So you'd get 2 Ce4 pluses to get the 2 electrons plus 2 Ce3 plus. All right, we see it happening here in this example. Silver and aluminum. The aluminum is losing 3 electrons. That means silver is going to have to gain 3 electrons, but the atom only gains 1. So we're going to need 3 atoms. So we multiply by 3. 3 electrons cancel, 3Ag plus aluminum forms 3Ag plus aluminum 3 plus. All right, so those are all of the different topics in Unit 4. Kind of a hodgepodge. The biggest takeaways from Unit 4, certainly stoichiometry, which comes into play with titrations. Being able to write out these chemical equations, being able to write out a net ionic, and there is some intro to acid-base chemistry and redox. So those are important. I know that they get expanded later, but they're in play now. So they're topics that are definitely fair game for the AP exam, even in a question that maybe is not designated a Unit 8 question. You may still see some acid-base reactions. All right, take care, guys.